Thank you, Justin, for the introductions, and a special thank to the Dean for the invitation to present today. And I will talk about my lab research on integrating machine learning and physics for intelligent cyber physical systems, which has a lot of bit of overlaps or relation with just the previous talk. Okay. So just a few words about myself and my research labs. I joined UCF just this semester in fall 2024 as a associate professor. And in my previous job, I am a recipient of an NSF Career Award, senior member of the IEEE, and have obtained some funding for my research. At UCF, my research lab is called the Intelligent Cyber Physical Systems, or ICPS lab. And my teaching is mostly focused on machine learning AI and system control theory. So my talk today is focused mostly on the research of my lab. So our lab research is focused on intelligent cyber physical systems. Cyber physical systems, or CPS, is a system that seamlessly integrates computation or cyber components and physical components, right? And the intelligent CPS, or ICPS, enhances intelligence in the cyber components of a CPS by integrating AI or machine learning to achieve higher performance, autonomy, and safety for the system. You can find examples of CPS and ICPS in many applications, from self-driving car to delivery robots to manufacturing automations and power and energy system, just as shown in the previous talk. There are many exciting opportunities of ICPS, right, given the recent advancement of machine learning and AI. But these opportunities also come with many challenges, especially at the interface between the intelligence, or the I, and the cyber physical systems, or the CPS. So our research is focused on addressing these challenges, and more specifically, what is the impact of machine learning on the overall system performance, right? How to guarantee the performance and safety of the overall system under learning. And in the other directions, how can the physics of the CPS going to inform the machine learning component to enhance its effectiveness and efficiency, and how to ensure efficient and secure computations of ICPS. Our lab, the ICPS lab, focuses on three main research thrusts. The first thrust is developing a theoretical and algorithmic foundations of learning control of ICPS. This is the bedrock of our research. The second thrust is applications of ICPS in smart and autonomous systems, such as smart buildings, robotics, and autonomous vehicles. And the final thrust is on building cyber infrastructures for ICPS, as we develop open source software tools and research infrastructures for ICPS, and also on education and training for these areas. Our research approach in ICPS combines four major domains: control, optimization, machine learning, and advanced computing. Our research has been funded by different funding agencies, including the NSF, the Army Research Lab, USDA, NIFA, and other sponsors as well. So we are very thankful for their support for our research. I will give an overview of our major research areas and results at a very high level, with the goal is to introduce our lab research and also to seek collaborations for our research. The first area is learning-based control, where the goal is to develop machine learning models of a physical process, and then develop a model-based controller using the machine learning model to control the process, subject to uncertainty and performance and safety constraints. We have developed a framework for learning-based control, starting from optimal learning, where we not only develop data-driven model of a physical system using machine learning, but also how to design optimal experiments to get the best, the most informative data for learning the models. And once you have a model, we use it in a model predictive control framework to control the systems, taking into account the uncertainty and constraints, and having probabilistic performance guarantees of the system. We can also combine these two components to develop simultaneous active learning and control to safely control the system while learning and updating its model from data in real time. We have applied our framework in different applications for modeling and controlling building HVAC systems, for adapting autonomous driving algorithms to different driving conditions, which is a major challenge in autonomous driving, or to learn and safely drive a vehicle at the same time. We also apply our framework for autonomous robots and robot networks. So we develop algorithms to learn and predict the motions of a dynamic obstacle to avoid them, and to coordinate a network of robots to optimally explore and learn data-driven models of a spatial field for environmental monitoring and sensing. Another research areas of our lab is efficient and secure distributed control and optimization, where we have developed efficient distributed computation algorithms for coordinating a network of robots. And in a recently funded NSF project, we developed methods to integrate machine learning into distributed optimization algorithm to reduce the edge communication and computations, and to make the system more efficient and more reliable. We have also developed methods for protecting cyber-physical systems from cyber attacks using fully homomorphic encryption methods and using differential sensor-based physically unclonable functions. So these projects are funded by the Army Research Lab. A current major research area of our lab is in physics-informed machine learning. In order to address some major challenges of using machine learning for CPS, especially for performance-critical systems, these challenges include the data inefficiency, where a machine learning model needs a lot of data for training, which may not be available for CPS. Another challenge is that these models are often prone to data quality issues, such as noise and missing data. And finally, these models are often not interpretable, and in many cases, inconsistent with physics, which may cause safety and performance issues. So the way we address these challenges is through physics-informed machine learning, or PIML, which is a framework for systematically and seamlessly integrating machine learning with governing physical law to improve the accuracy, robustness, data efficiency, and interpretability of machine learning models for physical systems. Right? So PML can be thought of as kind of a balancing between white box modeling methods and black box modeling methods. We have developed a method for physics-constrained motion prediction of vehicles, which can very accurately predict the motions of vehicles compared to other state-of-the-art methods by combining a physics-based model of the vehicle kinematic and then a machine learning model here. We also apply physics-informed machine learning for modeling building HVAC system, where we show using real data that physics-informed machine learning can achieve much better accuracy compared to other non-physics-informed machine learning methods, especially as small data sets. We developed a novel machine learning method called causal deep operator networks for dynamical systems, where we show using real data that our method could achieve not only more accurate predictions, but also consistent accuracy over future prediction steps, which is very, very important for control applications. We have applied our research in practical applications and deploy real-world systems. In the newly funded USDA NIFA projection here, we're developing fully autonomous drones in forest understories, which are very complex GPS-denied environments with very limited communications. The challenges that we are facing here are how to detect and avoid tiny obstacles in the forest understories, how to map and localize using only onboard sensors, and how to implement full autonomy using only onboard computing. So these are a simulation that is not shown here, but there is a video of our simulation of the drones. So these are very difficult challenges that we are addressing in this project. We have also developed and deployed real infrastructures, such as a distributed sensing and computing network infrastructure for research, which includes mobile robots, drones, not shown here, and wireless sensor nodes. And at UCF, I'm working with some faculty members to advise a group of students in F110s, small-scale autonomous racing. I've been using these F110s cars for both my research and my education efforts. We very much welcome internal and external collaborations inside and outside of UCF. Our capability for collaborations include our expertise in CPS, machine learning and control and optimizations, physics-informed or scientific machine learning, network and autonomous systems applications in robotics, energy systems, and others. We have ability and experience to develop realistic simulation of robots and to develop and integrate software for robotics. In terms of equipment, our